Okay, everyone, welcome to IME IME 765, and today is April the 6th. And let's continue the lecture about support vector machine. Today, I believe we can finish it, and then we will finish all the classification lectures. First, let me share my screen. And also, let me stop the video here. So, okay, which one? This is support vector machine, very good. So in previous two lectures, I introduced what is support vector machine. Basically, we try to find a separating hyperplane such that the difference of the two different classes will be maximized. The difference means the minimum distance from the data set from one class to this separating hyperplane. And the reason we can make it to be support vectors is because of what? Because we can use some algebraic trick to, convert this original bi-level optimization problem to a quadratic one-level optimization problem. And these constraints, annotate. Okay, I need my annotate board here. And these constraints are nothing but these two support vectors. Okay, so these are the meaning, the geometric meaning of this, and that's also the reason why we call it support vector machine. Okay, and now we also the one that I just introduced was a hard margin SVM, and we also have the soft margin SVM. The reason because in most applications you are not gonna find some kind of like accurate or let's say perfect data like this way. It's almost impossible like this. In most cases, my data will be somewhat like this. If this is the case, that means, let me see, I should say like this. If this is the case, then no matter how you choose your choose your separating hyperplane and the corresponding support vector machine, you will have some, let's say, classification points or some points which is inside the margin. Margin means the area between the two support vectors. Again, here we're talking about two classes. Okay, so the soft margin SVM gets the idea like this way. First of all, I use a CASI to be the relaxation, or let's say the slack variables for the constraints. In other words, I allow you to violate, to the number of CI for each data I. However, because CI is a relaxation or select variable, I want this relaxation to be as small as possible. Of course, CI are all non-negative. So I add a CI into my objective function, which is a minimization problem. And I can control or balance, the two parts by this C. So this part is what? This part, the smaller it is, that means what? That means the margin is bigger. Why? Because the margin simply equals 2 over, simply equals this here. So one side of the margin is 1 over norm of W. So from here to here, it is 2 over norm W. To maximize 2 over W norm is equivalent to what? Equivalent to minimize W norm square over 2, which is this, which is exactly this. So there's no difference. That's the reason why, come here. That's the reason why this one, if this part is bigger, then if this part is smaller, then the distance between the two classes will be bigger. I mean, between the two support vectors will be bigger. How about this part? If this part is big, that means your relaxation is very big. Of course, I want the distance to be big, so that I want this part to be small. And also I want the relaxation to be small, so that this part should be small. This C is a balanced parameter. Okay. Now, we also introduced the dual representation. The dual representation actually convert the original SVM problem to a much simpler dual problem, like this. The key difference is that if we have a look at the the original Lagrange function, then we have 1, 2, 3, 4, 5, 3 plus 2 decision variables. The first 3 decision variables are from the primal problem, and the second 2 and the last 2 decision variables of the dual variables, very clear. And then by the KKT conditions and some tricks, we can make it to be this way. And this L, let's call it, say, the Wolf Lagrange function. This one, I have only one decision variable, which is mu. And what? And this mu is actually a relaxed, sorry, this mu is actually a dual decision variable, makes our life much, much easier. And due to this and these constraints, I will have this. In other words, I only need to solve this problem for the mu. I can separate it already. See it? And this trick is very important. By the way, Mahbuba, you may, I don't know, yes or no, you may use this trick in your research as well. You compare this one with ADMM, see what are the difference, what are something not are the same. Of course, here I don't have any augmented part, but the trick something similar that I want to separate the dual versus the primal. Okay, the idea is the same. Okay, now from here, this problem is extremely easy to be solved using whatever, the current, let's say, method, the current technique for solving quadratic problems. Of course, for Mahbuba, maybe you like ADMM. This is extremely, actually, it doesn't matter. For this specific problem, who cares to use which method? It's the same, because really it's too easy. Okay, and now, after this, I want to get my W star and the W0 star, right? Because they are the keys for the SVM. Okay, now for the W star and the W0 star, the traditional method is what? The traditional method is that, suppose I have solved the mu star, because of this constraint, mu I star plus nu I star equals to C. So as long as I know all the mu stars, I know all the nu stars. So the traditional method to solve the primal problem is used this way. For a given nu star and a mu star, I'm gonna solve L of with respect to W, W0, and C. What I'm talking about is the primal Lagrange, is this one. I wanna minimize this for a given mu star and a nu star. But this is gonna be still kind of like time consuming. There's a method just by ON, the linear time, you can directly get to your W star and the W0 by what? By actually, again, substituting the result into KKT and take advantage of KKT, you will have all these kind of conditions, remember? And we introduced in the last time, okay? And then by 11 and 13, you can directly calculate W star and the W0 star. So I'm done. So the SVM is solved. After it, we introduce the kernel trick for the SVM that I can change this line to be curve rather than a hyperplane, because hyperplane, for example, this kind of data, it's really difficult to figure it out. And for the kernels, the trick is nothing but you change your x to be a function hx. And then since in all these, no matter the dual function or let's say my decision function, hx appears in terms of like this kind of inner product. So in other words, in many cases, I don't need to care what exactly hx itself is. I only need to care about the kernel function, which is the inner product of the hx and another, two different nodes. And we usually use three types of, especially the first two in machine learning, three types of the kernel function. The first is the polynomial function, the second is Gaussian kernel, and the third is a network kernel, neural network kernel, which is nothing but this kind of sigmoid functions. And then substituting inside, you're gonna get this. And then we showed examples, remember? So this is I think this example I use the Gaussian, right? Yes, I use RBF, I use the Gaussian. By the Gaussian one here, I do have one parameter which is gamma. And very clear, the bigger the gamma is, the more curved it's gonna be. If gamma 0, then it's nothing but linear, right? Okay. And for comparison here, I fix C. C is the parameter, is this parameter. Is a parameter, constant parameter in the soft margin SVM. We're all talking about soft margin SVM, okay? because in real applications, I mean, really nobody uses hardware, hard margin SVM because it doesn't work. You know, for almost all problems, it doesn't work. And then this is, no, sorry, it's here. Come back. Oh, it's here, okay. So here we fix C to be 1, and this is gamma equal to 0.1. This is gamma equal to 1, gamma equals to 10, and gamma equals to 100. And you can very clearly see when gamma is bigger and bigger, this kind of, you know, boundaries are more and more curved. In the beginning, it is not curved. This gives us what? Gives us a very smooth boundary. Smooth is good, varies. That means it's very reliable. However, this also has a problem that I have a lot of mistakes. You can see, you know, so many predictions, misclassifications. When gamma is bigger and bigger, our results looks better and better. For example, theoretically, you can prove gamma goes to infinitive. I will have what? I will have an unbiased classification or unbiased prediction. That means I will be absolutely correct. It looks very beautiful, right? But you have a serious problem that is overfitting. That the model you generate is junk. Why? Sorry for using this word, but why? Because the model that you generate works and only works for this specific group of data. You know what I mean? It doesn't make any sense because why you need to make the model? The model is not an art. Let's say, oh, I just run it based on this specific data, and I say, oh, it's perfect. It's 100% accuracy. I'm very happy. You're cheating yourself. It's meaningless. The model we want to make is to predict future data, right? You don't know where the future data is. If, for example, you make the model like this way, then what's going to happen? So suppose I have a feature data, which is, let me change the color to be yellow. Okay. Suppose my data is here. And we all know that, let's say, by our, you know, just intuition, we know that this one should be something like a red, right? Should be here. But have a look here. From this map, from this prediction, you see what? This yellow one belongs to blue, which is class 2. Then something's wrong. Why? Because you take your gamma too big and then make the boundary too tight, which means you fit your model too good, overfitting. We will discuss overfitting after all the linear regressions, probably in the end of April. I don't know, maybe in around 20 something of April. And then you're gonna see more things, especially the cross validation. Jody is not here, otherwise he's gonna be excited. Or what is overfitting? Okay, so here's a problem: how to choose the gamma. There's no general conclusion. It's a very, very data based. Usually you have to, you know, try different gammas and run, for example, a cross validation, and then you're gonna see which one would be the best. Okay, and in the second case, we fix gamma to be 0.1. And we work on C. C is what? C is a parameter to balance the two different objectives, right? So the first one is to try to maximize the distance between different classes. And the second one is to minimize the relaxation. And we can see with when C is greater and greater, what happened? When C is greater and greater, that means the model is more and more sensitive to a large penalty, to a large relaxation, right? In other words, when C is bigger and bigger, the relaxation items will be smaller and smaller. In other words, I would not allow, let's say I would allow less and less relaxation. And that's the reason why here you can see the difference is still relatively big, you know, between the red and the blue. But when your C is bigger and bigger, I would allow what? I would allow more and more difference, and a smaller and smaller difference, because I would allow the item of W norm over 2 to be bigger and bigger. Why? Because I have a large C. I don't really care about the distance between two classes. And in this case, you're going to see what? You're going to see that these classes, data from two classes, they're going to be closer and closer. But I do have very, very small panel, very, very small violations, this kind of relaxations. For example, you can see here, I guess maybe this is the only data. to get what the only data to get a misclassification. All others are correct. See it? While by comparison here, you have what? You have many violations or many misclassifications. However, the good point is that the boundary, or let's say the difference between the two classes are big. Here, the difference between two classes are smaller and smaller. So this is the kernel SVM, and also coupling with the C, the tuning of the C. Any questions so far?
So I have a question here.
Mm-hmm. Yes.
So increasing both gamma and C,
mm-hmm.
I think the results are similar. We have a better classification. I mean, the less misclassification and less error.
The results are similar. They're very different, right? Look at this and this. Don't you feel very, very different?
Yeah, but I mean, when we increase both of them, we decrease the misclassification, or we decrease the error, isn't it?
Yes. If we, you mean decrease? You mean increase or decrease?
Decrease misclassification. When we increase them,
you increase this data and also you increase that data, you're gonna decrease the misclassification, correct?
Okay.
However, there's a problem, especially for this case. From this specific picture, you can clearly see what? You can clearly see if you increase this one, yes, misclassification is decreased, but also what? Also, you have a serious problem of overfitting. See it?
Yeah. So my question is, which one is more important to adjust?
Good question. In general, you don't know it. Nobody knows it. Which one is more important? It's a very, very data-based. Different data would give you very, very different conclusion.
Okay.
This is called a bias variance trade-off. Let me show you another one. This is lecture 5, I think, about KNN. This is about KNN, and you can see here, bias variance trade-off. In KNN, we have exactly the same thing. See it? When that is, how would you choose the K? The different K will give you something very, very different. For example, here, K is 1, K is 50. You can clearly comparing the difference. When K is 1, it's more accurate, but it's less smooth. When K is 50, it's less accurate, but it's more smooth. More smooth means what? More reliable. That you can apply it to more, let's say, more data set. Less smooth means more accurate, but you need to be very careful because it could be overfitting. See it? The same. And here's some proof, something interesting. But this proof, this specific proof till here only works for KNN, because otherwise, I think this part is still correct. What I'm talking about is 2. This 2 works for any data set. But from 3 to 5, these conclusions works for only KNN, because here I use the KNN model. You can definitely put the F of SVM inside, and then you're gonna get your conclusion. But conclusion usually it is the same. That if you increase your smoothness, then you're gonna decrease your bias. Using simple words, it is if you make your boundary to be tighter and tighter, to be very tight, very, very close to your training data, then yes, your training result will be very good. However, they are not reliable. In other words, you cannot guarantee that this data will be working for other data sets. For example, you can have some very terrible results like this. Oops, like this I'm talking about. You know what I mean? Because if you have this boundary, probably you don't trust it. Because it's seriously overfitting, very clear overfitting. Only works for the data specific. Only works for the specific training data. If I have a real data, for example, here or here, very clear, they are wrong. So that's it. In general, there's no conclusion which one is better, or let's say which parameter should I tune. In general, I don't know the answer. I mean, it is really, really example dependent, the answer.
Okay, thank you.
You're welcome. Any other questions? But this is a very good question, Said.
No.
No? Okay. Let's have a look at today's main topic, one of the main topics, it is SVM model for more than 2 classes. Previously, we've introduced SVM models for only 1 class. But in many cases, the SVM model, in many cases, we could have more than 2 classes, right? Can we run the SVM? Yes, we can do it. How to run the SVM? We have many different methods. Here, I introduced the 2 most famous ones. They are the one against all method and one against one method. And be careful that these 2 ideas are not only for SVM. These ideas are for many different things in statistics or even in Bayesian inferences. You will see a lot. Okay, so regarding the SVM one against all model is in this way. We're talking about soft SVM again, because the hard margin SVM is just a special case, okay, of soft SVM in which C equals infinitive. Okay, so the objective function is the same, but the constraints will be different. How different? So for each feature, for each class, I have a what? I have a SVM model. It's specific SVM model. This constraint works for the data whose label is whose label is K. And this constraint, let me use another color, works for the data whose label is not K. And you're gonna, just solve all the models, and you're gonna solve M models because what? Because I have M classes, not features, classes. Okay. So what does it mean? Have a look at here. Why it's called one against all? The reason is because here for each the case SVM model, right? This is the one, and this is the all. See it? I'm gonna use the case class to be against all other classes. So very clear, this is one against all. And so totally, how many models do you have? Let me see, can I add a text here? Oh, really? Okay, good. So
totally,
sorry, yeah.
So you mean we consider, so you mean when we have M classes, we convert the M classes to the 2 classes by
somewhat like this. Yes, you can somewhat understand it in this way, correct?
Okay.
Yeah, because very clear, I just classified to see whether the label is K or the label is not K, right?
Okay.
So totally how many, go back. Okay, totally how many such SVM models do we have? We should have N, because for each class, I have 1 SVM model, right?
Yep,
okay, and then we solve it. And then, so after solving all of this, how would you predict the label of a target data, a new data X? So for a new data X, we're gonna predict the label in this way. We are gonna calculate all the FKX. The FKX is defined by this way. Each FKX is, the model for WK, which is WK star, and the model for WK0 star. And I'm gonna substitute this WK star and WK0 star into my decision function. And then I'm gonna take which one gives me the biggest value in the decision function, and then I'm gonna take it, predict to this label. Any questions here?
No.
Why we take the max?
That's a very good question. Why don't we take, for example, absolute value max, right?
Yep.
Okay, that's what I wrote here. Yes, you may say, hey, why it is max? Why not, for example, minimum? Or let's say the better one might be absolute value max, which is fair, right? Okay. We actually don't need absolute value here. Why? Compare this one. Let's say this. Suppose K equals to 2. M equals to 2. Remember, we want to compare this model with the model that we introduced, the very standard 2-class soft margin SVM model, right? Okay, so they should be correct. They should be the same, clearly. Otherwise, something's wrong. But don't forget that I have a difference here. That in the previous model, I only have 1 W and 1 W0. Have a look at the model here. Suppose M equals to 2. What do you have? You are going to have yi equal to, let's say, k, and yi is not equal to k. Here I have what? I have a w k1. Sorry, I should say I have a w1 and a w2. See it? Suppose k equal to 1, 2, and 2. Okay, I should have a w1 star and a w2 star, right? And also I should have a w10 star and a w20 star. By comparison, you will have two models here. If you really compare these parameters clearly, you're gonna have that your w1s. Give me 1 second. Let me see. Yes, that's correct. You're gonna have w1 star equal to w2. I should have a star here. w1 star equal to negative w2 star, and the w10 equal to negative w20. You know why? Because these two constraints will be the same. The only difference is a negative side, a negative size. So if you list both models means for the case of k equal to 1 and the case of k equal to 2, in the case m equal to 2, then these two actually gives you the same thing, that w1 star equals to negative w2 star, w10 equals to negative w20. And hence, that's the reason why you're gonna see what? You're gonna see a negative here. You know what I mean? That's something exactly as what you saw before. You're gonna see whether this one's gonna be positive or negative. If it's a positive, then I'm gonna take, for example, class 2. If it's negative, then I'm gonna take class 0, right? This is exactly the same meaning. What you're gonna do here, that if it's a positive, you're gonna do class 2. And then what you're gonna do is that, for example, you're gonna use this positive times negative 1 here and here. Then you're gonna see another negative 1. You see what I mean? So in other words, what you need to do is to make the absolute value and see which one's bigger. You're gonna choose which one. You see it? That's the reason why if m equals to 2, you compare this model with our traditional soft margin SVM model, they are gonna be the same. In other words, yes, by comparing the maximum of the decision function, it is correct. It is the same as we compare whether it's negative or positive and then make the decision for the two class SVM. Any other questions? You just need to, after the lecture, you just need to have a look at this. List the two models, because for y equals to 1 and y equals to 2, compare the model with this model. And you're gonna see they're the same. The thing is gonna a bit be different as w1 star equal to negative w2 star, and the w10 star equals to negative w20 star. That's it, which equals to the w and the w0 here, your traditional soft margin SVM. And that's the reason why previously we said, okay, find the negative or positive, and here we say choose the maximum one. That's the reason. Any other questions?
No.
Okay, and similar, if you don't like the hyperplane, you want something curved, something cool, then you can use the kernel function, hx, put the h here instead of the x here, and everything should be working as well. Okay, so the second method is called one against one. So one against all here is for each SVM, sorry, for each class, I have a specific SVM model, and I'm gonna use this one to be against for all other classes. As as Said just said, it's something like 2 classes. For the one against one model, it is for each pair of the classes, say class K and class L, I'm gonna have 1 model. So totally, how many models do I have?
And 2.
Totally. Sorry?
And 2 models?
Yeah, m choose 2, right? Which is m times m minus 1 divided by 2. I should have so many models. I wish they can have the LaTeX editor so that I can also write the LaTeX here instead of writing the word. Okay, so total I have these models. Clearly this model is more than here, right? But the good point is that here it's easy. Why? Because you only have 2 classes. It's not gonna be like here. Here I will have 1 class, and here I have totally m minus 1 classes. It's gonna be very, very crowded in this constraint. Here it's relatively easy. Why? Because for each constraint I have just exactly 1 label. You see what I mean? so that it is the case that I have more models, but each problem will be smaller, would be easier. Okay, so, and let me go back here. So this is something idea. Why it's idea 1 versus 1? Because here you're going to compare the pair of class K and class L. K versus L. See it? Okay, so you're going to solve all these models, all these M choose 2 models. Okay, suppose everything is solved. Then how can you predict the label for target X? Here we're going to use, come on, go back. Here we're going to use a scheme, a system called a maximum win system. So the max win system is in this way. I'm going to solve all the models here so that I'm going to have all the W stars, right? And then I'm going to add 1 voting score to class K. If I compare, the KL, I get this one is less than or equals to 0. If KL is greater than or equal to 0, then I add 1 point to the voting score of class L. Then I'm going to do what? So I'm going to do all this so that totally each class will have its own score, right? Because each class, they are going to be used to compare with other M-1 classes, right? So totally I will have the score for, so finally I will have the score for each classes. And I predict the label by, oops, here's a typo, L-A-B-L-E. In writing the latex, I always write L-A-B-L-E instead of B-L, and then finally citation error. Anyway, I don't know whether you have it or not. And so here, I'm gonna predict the label by the maximum voting score. So in this case, yes, I can find, I can predict my label. I can predict the label for target data. And be careful here that what I wrote is KL less than or equal to 0. This is KL greater than or equal to 0. So suppose in the real case, you have exactly equal to 0. So under this system, you're going to add 1 point to both K and L classes. Of course, in some other cases, they may write strictly less than 0 or strictly greater than 0. In other words, if it's a 0, you're not going to add to any class.
When I have a question.
Yes.
When FKLX is 0, it means that
both.
That specific X is on the separating hyperplane.
Yes, exactly. No, be careful, Saida, be careful. It's not necessarily separating hyperplane. Why? Because of this. You can use kernel. But this must mean exactly on the decision boundary. This is correct. The decision boundary between class K and class L.
So you mean, so in the case that FKL of X is not 0, so we consider one of the classes as positive 1 and one of the classes as negative 1.
Yes.
And then we put the X on the separating hyperplane function that we have. So based on the value that it gives us, we actually classify it as class +1 or -1.
Something like this, but be careful here. The difference that something like this. You can understand it in this, but strictly you cannot directly denote it in this way because each class should be coded individual. I should say each class should be coded uniquely. You know what I mean? Because your class label 1 in the KL case doesn't mean the class label 1 in let's say K, let's say whatever, let's say KI case. You know what I mean? They're different. So what however, for if K and L are fixed, then yes, you can use this idea to understand it, which is if this one is less than 0, just found another table, a lot of small typos here. If this one is less than or equal to 0, then it belongs to X. Then it belongs to K, so that you're going to add 1 voting score to K. If FKLX is greater than 0, then it belongs to L, so that you're going to add 1 point to L.
So I have a question here. Is it a convention that we have a convention here that, for example, if it's less than 0, it's in class K. If it's bigger than 0, if it's in class L. It's something that we set. We can set the other case, isn't it?
Yeah, of course. But you have to, of course, because it doesn't matter which is K, which is L. You know what I mean? That's just the case. For example, in the two class, I said, oh, -1, then it's class 1. A +1 as class 2. Why? If you like, you can set. You can reverse it. It doesn't matter.
Okay. Thank you.
Yeah. But be careful here. We cannot say that because if this was less than equal to 0, then it's class K. No, you can only say that the data prefers class K to class L. You know what I mean? Because this is 1-to-1. This is a 1-to-1 against 1 model. What you can say is that in terms of K classes, K and L, it's more likely to be in class K. That's the reason why we need this max win voting scheme. Okay. Finally, whoever gets which label gets the maximum score, voting score, we're gonna predict the X to be that label, that class. Okay. You know what I mean? So this is different from here. From here, I don't need to vote. I just one time done to see whichever is the maximum one. I'm done. But here it's a voting. Why? Because you are running a 1 against 1 model. Okay. Any other questions? I will fix these kind of small typos after the lecture. Any other questions? No? Okay. So here's everything about the SVM. So and also I believe here's also everything about the classification. I mean the main topics about the classifications. And after it, we're gonna go to regression. For the classification problems, oh, I forgot one thing. That last time I said that we're gonna run some data, play for fun, right? I forgot about this. I will try to do it in the next class. I wish I remember. So for these kind of things, first of all, you'd better understand these kind of mechanisms or the principles behind it very clear. The reasons because in many research, it's not enough. It's not enough just to run this kind of apps or this kind of for example, use the Python. You can import the libraries and then use the libraries. There are a lot of packages or a lot of functions that are already compiled, already made. It's not necessary in many cases, and you have to develop your own model. And if you have never known this kind of knowledge background, it's not important. It's not almost not possible. It's not at least not likely for you to easily design a model. You know what I mean? So that's the point number 1. Point number 2 is that don't you think kind of like just simply running this kind of packages, running this kind of apps are too simple, right? I remember several days ago I shared a link which is actually an MIT professor in grad level CS class. By the way, he's a very famous professor introducing the SVM. I don't know, have you checked it or not? If you have checked it, you're gonna see the same type. For a grad level class, you need to know the background very, very clear. Why? Because to know how to run code it, maybe it takes you just several minutes. For example, in the MATLAB, I do have a tool, MATLAB classification tool, toolbox. You just click it, and very simple. You just choose, oh, where's your data, and click down. Everything's going to be trained.
The MIT class, is the teacher is a bald guy?
Sorry, the what?
Is the teacher a bald guy? Bald guy.
I think so. Yes, he's a very famous professor. And then you feel free, really, click inside. Feel free to compare the content with my SVM content. First of all, he's really an excellent instructor. But if you compare the content, and maybe you're gonna feel that seems that I include more things inside. And the point is to let you know that a machine learning class should be in this way. You know what I mean? It's not something that just running applications. In the next class, again, if I have time, I'm gonna run some application to show you how interesting it is. Then you can play it for fun. And also, that's very simple. You just need several minutes, and you're gonna learn it. Okay, now let's go to lecture 9. Is this lecture 9? Great. Linear regression. In this linear regression, before introducing it, I'm going to tell you that I'm going to include the statistical inference of linear regression here. And also, I'm going to include the Cholesky decomposition and the QR factorization. Okay, and if you don't know it, I would strongly recommend you have read this before Wednesday, let's say. Otherwise, you may feel very painful because it includes a lot of mathematics. For Mahbub, I think you should be very comfortable with this. Otherwise, there's going to be a problem because last year in June, you did a topic, something.
Yes, I know.
Especially the QR and SVM, okay? No, not SVM, SVD, singular value decomposition. Because there we introduced what? We introduced a pivoting, a QR factorization with pivoting, okay? Okay, so let's start here. Today, I'm not gonna introduce Cholesky decomposition and QR factorization, no time. Okay, so basic linear regression models is this. I'm gonna go here very fast because we've already mentioned it many times. First of all, I have a X and a Y. So linear regression means that I'm gonna use this linear function to predict my Y. Of course, I don't know whether they're really linear or not. The linear regression means I assume they are linear. Of course, how would you assume? Usually what we do is that we're gonna, for example, draw some points. And if it is low dimension, the feature is low dimension. If the feature is high dimension, the very first thing, we're always gonna try the linear regression, okay? And it's gonna be in this way. So what you wanna do is to figure out the beta 0 and the beta j. That's it. Be careful here that here, because I wrote it as y hat, indicating the estimated y. And this x could be a random variable here to predict the in output y, okay? Something I do need to mention are here. These axes could be dependent rather than independent. And in many cases, in some cases, not many, in some very unusual case, you may see that these axes could be very dependent. For example, in some cases, you're gonna see the x would be what? The rank will be much smaller than the size of x itself. Here we assume totally I have n records and p dimensions, features. Note that in most previous lectures, I use n and m, or m and which means, let me see, which means I have n data and m classes, right? Here, the reason I use n and p is because it's too famous. It's for example, QR factorization. Why you use k, QR? Why don't you use a, b? You can of course use a, b, but people tend to use QR because everybody call it QR. You know what I mean? Similar for linear regression, especially later we're gonna say lasso and the ridge, regressions. Everybody says when the case n is greater, when the case p is greater than n. Very few people say n is greater, m is greater than n. That's the reason why I want to be consistent to other, professors' books. That's why I use the number of columns to be p. Okay, actually p plus 1, because if you consider this beta 0. Okay, then let me show you a very simple but very interesting. Come on, huh? Go. What happened? Oh, because of this. Go back. Okay. Let's have a look at this. American flag. So we're in the US, so everybody knows American flag looks like this way, right? Question, how many stars? Do you know it?
52.
52? I think 50.
Number of states?
Right? I don't know whether it's 52 or 50. Okay.
We have 2 states out of United States territory.
How many stars in American flag? 50, you see.
Oh, okay.
Yeah, but that's a good question. Why not 52, right? I believe we do have 52 states. Anyway, but the point I want to say is that suppose this is X, okay? How many columns, how many rows, right? Let me ask you, what do you think about the rank of this picture, of this X? Suppose X, the dimension is n by p. Let's suppose that n, okay, it doesn't matter. Here, actually, p is greater than m. Okay, so we know that the maximum rank that matrix X can have equals to n, right? equal to minimum of n and p, which equal to n, right? But do you think the rank would be n? Actually, the rank will be very, very small.
Could be less than m.
Not could be, but much less than n. Why? Because there are too many repetitive patterns. For example, see, line, line, line. They're the same. Star, star, star. They're the same. See? Maybe that's the reason why they put it to be 50. Because if it's a 52, it's difficult to be divided. 1, 2, 3, 4, 5, 6. No, it's also not divided. 1, 2, 3, 4, 5. Okay, here's 5. Here's 6. But in that case, that's 11. Right? 11 times what? Oh, yes, 11 times 4 equals to 44 plus the last row 6. That's the reason why it is 50 instead of 52. Otherwise, where should we put the other 2 stars? Maybe they're going to make this part bigger to put one here, maybe. I don't know. Anyway, but the point is that this X will be very, very small rank. Okay, and there's one very important problem is something like the image recognition, or let's say the image processing is that suppose, okay, for example, where's my annotated board? My annotated board is here. So let's make example. Suppose this is the American flag, but I take this part out. What I mean this, I need one field one. I take this one out. Okay, and this is the American flag that you can see. And I want to ask you to recover this flag. How can you recover the flag? And this is a very, very famous problem, which is called, good question, Mahbuba, which is called what? What is the name of this problem?
Pattern recognition.
Pattern recognition is too big. Why don't you say operations research?
It is called
minimum something.
Matrix completion.
It is, yes, it is matrix completion, but this technique is called minimum rank. Okay, minimum rank optimization. That you want to recover a matrix such that the current known ones are still here, but you want the rank of the matrix to be minimized. To do this, what we're going to do is that we usually yes.
Sorry to interrupt you. So condition would be like the matrix should be positive definite or negative definite, like that, right?
Which one? This one? No,
so
it's impossible. It's impossible.
In matrix completion, low rank matrix completion problems, sometimes we make assumptions like matrix should be positive definite or negative definite.
No, it's impossible. There's wait. There's one possibility. Yes, one possibility is that for the smallest matrix that we can figure out, and then yes, you can assume it to be PD, or let's say negative to be PD, which is negative definite. But for the whole matrix, it's impossible. Why? Because the matrix is a rank deficient. Once rank deficient, for sure, it's not gonna be PD for sure. You know what I mean? So that usually what we fix is that, so for the observed ones, it should be accurately equal to, we want to recover this, we want to have another matrix. For example, the true matrix is called, for example, let's say M. My new matrix is called X. First of all, for all observed ones, the Xij equal to Mij. Second, the whole matrix, the whole X matrix, I want the rank to be as small as possible. Why? This means I'm going to repeat the patterns. Okay, so for these kind of problems, your X could be rank deficient and could have problem. And we have a very small part, which is lecture 4, not lecture, sorry, which is I believe section 2.3 or 2.4 something here in the last, let me see, which is here. We have a very small discussion, and regarding this part, it's a big research topic here. For example, you can use the Euclidean norm. You can sorry. You can use a Euclidean norm. So sorry, you can use a nuclear norm. Sorry about that. You can nuclear norm, or you can use let's say 1 norm, 2 norm to make a regularization, you know, and then you can use a trace and then reformulate it to trace problem, and later you can have an equivalent reformulation to prove that that's equivalent to convex problem. And in some cases, it's not only convex problem, it's SDP, semi-definite programming. That is, I remember, what is her name? A very famous lady. She got that part in her PhD dissertation, and that's an excellent research finding in 2006, if I remember correctly, because previously people can only, you know, estimate it and try to, you know, pure estimate using numerical method. And she proved that one type of the problem can be equivalently formulated to be an SDP. Usually people use trace, this kind of trace technique to formulate it. Anyway, all these are too far. But here, just to let you know that this X could be dependent. Why? Because as I closed it already. No, it's here. For example, this American flag, for example, this row is the same as this row, so that they could be, the X could be dependent. Another case for the dependent X is we can code something. Remember, it's here, lecture 2.1 of section 2.1 of lecture 7. Let me open it. Lecture 7, LDA, what is that? What is this? Oh, no, sorry. This is the one I wrote inside. Okay. Section 2.1 is it's right here. So right here, I think so. Yes. So here we introduced. No. Section 2.1 quadratic, right? QDA, and we included an example here. See it? What we did is that we code the 2D data to be 5D data, in which x3 equals to x1 times x2, x4 equals to x1 square, x5 equals to x2 square. See it? And we compare this, the LDA. We compared this, the coded LDA versus the QDA. Remember this example? So in this example, actually, you see what? X4 is related with X1 and 2. X5 is related with X1. X3 is related with X1, 2. X4 is related with X1, and X5 is related with X2. See it? So in this kind of cases, I code the X. So of course, they must be related. And another thing is that, for example, for classification problems, I'm going to code the category. For example, class 1 means -1, class 2 means +1, for example. So, and we use an indicator function, okay? So in this case, this X could be only integers, for example, only 0, 1, or only, let's say, +1 or -1. So all these inputs are valid. Don't feel weird to say there's only why it is X is not a continuous variable, y X is only 0 or 1, or y X is kind of like some X's are dependent. Yes, there's no problem. All of them are valid. Be careful, here we're talking about linear regression, a little bit different from ANOVA. Have all of you learned ANOVA?
Yes.
Okay, very good. Said, have you learned ANOVA?
Yep.
Okay. So the difference is that here, first of all, I guess you have learned the linear regression expression of ANOVA, right? First of all, ANOVA can be completely expressed by linear regression. But the difference is that ANOVA wants to tell, let's say, the difference of, let's say, the variables. I'm gonna have an analysis on the variances of different variables. So usually in ANOVA, what we want to see is that all decision variables are independent. That's what we want to see. But in linear regression, there's no guarantee. For example, as I just mentioned, you can definitely code these variables let, for example, x3 equals to x1, 2, x6 equals to, for example, x4 squared plus x5, so that they're dependent. And I don't care. You know what I mean? Okay. And now, similar, let's use D to be the decision, sorry, to be the training set, the training set. And again, I have N observations, and I have P such axes. And to make my life easier, I make my matrix form which y is a vector of Rn, x is a vector of Rn by p plus 1. Because I make the first column to be 1, to make my life easier. And the beta is a vector of p plus 1 because I include the beta inside. So these two, formulation 2, can be easily written as y equals to x beta vector form. Very concise, very beautiful. And clearly, once I know beta, I'm done. The question is how to figure out the beta. Regarding this one, I've also mentioned many times in previous lectures. What you want to do is actually to what? The so-called least square regression. So here's the illustration figure. I want to have a line such that the squares of these kind of differences or the distances will be minimized. And so that we're going to minimize the residual sum of squares, which is this, where my RSS residual sum of squares is defined to be the norm, squared norm of y minus xb, which means the summations of all these distances. Okay, these are things very simple for you guys because you are PhD students. Okay, now following basic things, basic method, I'm gonna do what? To minimize this part, what shall I do? Gradient, right? Or make the derivative. So I'm gonna make the gradient of beta, well, the gradient with respect to beta in RSS, and set it to 0. So this we've done many, many times. Okay, I'm gonna go it very fast. So this gives you a negative 2x here, beta, and then copy and paste this part, and then you're gonna solve it. And then I have this part. This is called ordinary least square solution, OLS. Let me ask you a question. Why it's called ordinary? So which is parallel to ordinary? Do we have some other least square, linear least square methods? You should have learned. Generalized least squares, GLS. Okay, but in this lecture, let's make our life easier. For most cases, I'm gonna introduce the OLS. Okay. Okay. However, if you have multiple outputs, that's another story. Okay. Now let's have a look. If I want to say this part is, oh, okay. Let me write down something. Here's something important. Let me open my Word. Where's my Word? Okay, good. So what we have here is we have this 7b. 7a is too simple, which is nothing but the derivative of this one, okay? 7b gives you this, gives you xtx beta equals to xty, right? All these are vectors, so let me make it bold. And from here, you get what? You get from beta equals to xt x inverse and then x ty. Okay, I'm lazy to make it all bold. Just as long as you know all of them are matrix or vectors. But there's a problem. What is the problem? How do you know this one is invertible? XTX is invertible. And here we need an assumption that X is a full rank. Question, why if X is full rank, then XTX must be invertible? Why? Can anyone show me a simple proof? Seriously? This one, you guys should immediately tell me the answer within 5 seconds. That X invertible, so of course the yeah, invertible means the what inverse matrix exists. Really, invertible is spelling it this way. Okay, I always use TABLE. How do you prove it?
Can we use eigenvalue decomposition to show that X can be?
Say, you know what? If you don't know it's invertible, you cannot guarantee eigenvalue decomposition exists.
Okay.
So of course, if you know it is
that is
invertible, you
not
can use eigenvalue decomposition, and that's what I did actually later, which is something I showed here, right here in the statistics. But first, you need to know this is invertible. Otherwise, you cannot do it. You know what I mean? Yeah.
Yeah.
A super simple way. The truth is that if X has a full rank, this one must be PD, not PSD. I'm talking about PD. Okay, positive definite. Why? Consider this. For any vector U, this vector, we have what? We have, let's say, UXT, UT, sorry. UTXT X U. This equals to what? This equals to X U T X U, right? My last name, Greg. Okay, so now you know what? This one must be greater than or equal to 0, right? Right?
Yep.
Okay, but there's a problem because I said it's a PD. That's not enough. You want to say this one is strictly greater than 0, right? Of course, if U is 0, you have to be 0. So I'm going to write it not equal to 0. U is not 0. If that's the case, then I must have this one greater than 0. Why? Anyway, due to time limit, let me directly tell you the answer. But indeed, all this you should be able to know it already because these are really undergrad level. So the reason because X is the full rank, so that XU equal to 0 has only one solution. U equal to 0. And now U is not equal to 0, so that XU must be greater than 0. Okay, clear? So, or you can say, let's say the null space of X equal to 0. That's it. 0 vector is the only element in the null space of X. So, if that case, this shows that X is XTX, XTX is PD. And hence it is invertible. No, again, invertible. Okay? That's the reason why, as long as I say that matrix X has full rank, so this must be invertible. Okay, and this is actually the other side is also correct. If this is invertible, then your X must have full rank. Why? Because if it's invertible, that means this must be PD. If this is PD, that means what? That means you must have this greater than or equal to 0. That means this one must be greater than or equal to 0. That means the only solution for this one, XU equal to 0 is U equal to 0. That means what? That means X has a full rank. Okay, so they're equivalent to say that this one has PD as PD or X has full rank. They're equivalent. Now, since this one is invertible, I have this. Of course, I can, this one exists. Another thing is if we have a look at the Hessian matrix, which means the gradient of the gradient of the RSS, now we have, then we're gonna have what? So we're gonna make a derivative here with respect to beta again. What do we have? We have nothing but XT, XB, right? Again, we just mentioned that XTX as positive semi-definite. This is this notation. Remember this one? This notation, it should be P plus 1. I always get confused with P and P plus 1 because of this. Because I have one here. Sorry. Write it to be P plus 1. I'm gonna correct it. It's gonna be PD, right? because this is a PD, so this tells you what? This tells you, yes, this solution is really what? A global minimization. Why global? Because it's clearly this is what? This is convex. So this is a convex programming. So the local minimization means global minimization. Okay, so this tells you, yes, this is the unique global minimization, and we call it OLS solution, ordinary least squares estimator or solution, whatever. Okay, and of course you just substitute because your y equal to what? Your y hat equal to x beta hat, right? You substitute it inside, and then you're gonna get this one. Okay, all these are very simple. However, other than this very, very simple numerical, or let's say algebraic, derivation, I want to show you a geometric interpretation. This is extremely important. I think I still need a word. Okay, first of all, from this one, what do we have? We have another thing is geometric interpretation of the OLS solution. Okay. From this, let's say xt y minus x beta equal to 0. This tells you what? This tells you that this tells you this. XB is what? XB is y hat, right? And y minus y hat is what? As
is the error.
Yeah, error. This tells you that this B mean what I mean. This B is the B hat. Okay, strictly this should be B hat. Okay, let me put it here. Oh, come on. Okay, so this actually tells you that y minus y hat should be what? Should be vertical, should be, how to read this word? Perpendicular to x. This x means the space spanned by x vectors, x1, x2. Have a look at this picture, this figure. Suppose here I have only two axes, x1 and x2. So x1 and x2 spans one figure, one plane, right? The plane is this part. And now this is your y. And your y star equal to what? Your y star equals to x times beta. And this tells you that your y hat star, your y hat, which is the estimated y, use y minus y hat, which is this line. This line must be perpendicular to x, must be perpendicular to this plane. See it? The plane spanned by x1 and x2. That means what? That means yes, it's gonna be in this way. It's not gonna be, for example, in this way. For example, let me. It's not gonna be, for example, in this way. Okay, no. I need. Okay, what happened to my word? Okay, I need another color. Let's say use a blue color. It's not gonna. Let me use another. Let's say green color. It's not gonna be in this way. Why? Because this arrow means what? This arrow means what? This arrow means y minus y hat, right? This is y hat. And you need to guarantee that they are perpendicular. See it? That's the reason why you must have this. And this is also the reason why we call it a projection. Maybe in many books or in many other lectures, professors call it a projection. Why this is a projection? Because of this geometric interpretation, okay? This means I project it onto this plane, which is spanned by x1 and x2. See it? Okay, so this is a very, very, very important interpretation of the OLS solution. The orthogonal projection of the output data Y onto the subspace spanned by, you know, these x vectors. Okay. And so, okay, lucky this time I wrote it p+1 rather than p. Here I wrote it to be p actually. Okay. And another thing I want to mention is that remember in the logistic regression, still remember the very magic IRLS algorithm that I showed on the whiteboard. I missed my whiteboard a lot actually. At that time, let me open it. Lecture 6, logistic regression. Where's my logistic regression? Oh no, not here. It's here. In the logistic regression here, we introduced IRLS, and we indicate that this is nothing but the solution of this one. See it? And this is called weighted least square problems. So the basic form of the weighted least square is in this case that I have a weight, which is positive weight, of course. We denote it as square root of WI, and this problem can be equivalently written as this matrix form, okay? And this one is equivalent to be this, of course. Now you do the same thing. You make the what? You make the derivative with respect to beta, and then you're gonna have the corresponding OLS, but it's a weighted OLS, and this equal to this. And this is very easy to be verified. You can just do it by yourself. You know, this gives you what? This gives you a negative xt, and there's a 2, and then times w, and then copy and paste this one, and then you solve the beta. You're gonna get this. Okay, and again, as long as your x is positive semi-definite, as long as your x is full rank, this one must be what? Must have full rank, so that it is invertible. Why this is true? Because your W here is an diagonal matrix, okay, in which all the WIs are positive. Okay, now suppose you have this, you have a U and you have an X, you have what? Another, okay, let me write it down, it's easier. Where's my Word document? Let me directly write it down. Sometimes writing it down is much easier than directly to say it. Okay, now suppose for a U is not 0. You're gonna have what? U times, where it is? You're gonna have U times X T W X U UT. This equals to what? And be careful that my W is a diagonal matrix with all elements on the diagonal elements are greater than 0, so that I can decompose this one to be this way. Okay, and then this equal to what? This equal to this. This equal to this. Anybody knows why? Because W is a diagonal matrix, so WT equal to W. That's it. Super simple, isn't it? Okay, and this is clearly greater than 0. Why? Because U is not 0, and also because X is full rank, and the W is what? W is a diagonal matrix with all positive items. Okay, so this shows you that the inverse matrix exists. Okay, so this solution has no problem. So these are some very, very basic things, mostly the motivation of the model and also the OLS solution. Any questions? No? Okay, great. It's 4:15. So this is the end of this lecture. Let me go back so now you can see me. This is the end of the lecture. Thank you very much, and I'm gonna see you on Wednesday. If you are not familiar with QR factorization and channel scale decomposition, let's say it's your first time to hear this, please have a look, please read this, the Chatelsky decomposition and also the QR factorization by yourself, because I guess I will finish, I don't know, but I will try to finish the Chatelsky decomposition in the next lecture, okay? And you might feel a bit painful if you have never seen this, because it indeed has a lot of matrix notations like span, no space, range, and also the what is called the complement space about this. A lot of math is gonna be here. Okay, that's everything. Have a good day and see you on Wednesday. Bye bye.
Thank you. See you.
Thank you.
Bye.